Next up, let's take a look at some probability problems that involve the word and. In all these problems, two different things are going to be happening, and we're going to look at the probability of those two things happening together. Just like before, we'll look at a practice problem, then we'll talk about some of the details of and probability, and then I'll invite you to try one more problem. First up, what is the probability of choosing a chocolate and not coconut candy? Chocolate and not coconut. We could do this visually by counting how many candies are both chocolate and not coconut. Well, that's this one, 2, 3, 4, 5, 6. Remember, we wouldn't count a candy that had coconut in it because we're looking for not coconut. And we wouldn't count one that was not coconut if it didn't have any chocolate. We want chocolate and coconut together. This could also be done using a two-way table. First, I'd like to shade all of the candies that are chocolate. Next, I'd like to shade all the areas that are not coconut. Now, if I want to know which candies are chocolate and not coconut, that'll be this 6 here, the area where chocolate and not coconut overlap. But how would that look on a Venn diagram? Well, first, I'll need to shade in all the area that was chocolate, just like before. Remember, all the candies that are chocolate are inside this circle labeled chocolate. Next, I'll shade all of the area that is not coconut. Remember, all of the area that's not coconut is outside of the coconut circle, shown here in this fuchsia color. Then, to find where I can have chocolate and not coconut, that's where those two colors overlap, or the 6. So any way you look at it, there are 6 candies that are chocolate and not coconut out of a total of 12 candies. So the probability of choosing a chocolate and not coconut candy is going to be 6 out of 12, which can be written as 1/2, as a decimal, that is 0.5, and as a percent, that is a 50% likelihood of getting a chocolate and not coconut candy. Now let's fill in a few of the details here about and probability. Anytime we're looking at and probabilities, we can also use the word intersection. Now this makes sense because when we're finding an and probability, we're literally looking for where the two shaded areas intersect. Now we write the probability of A and B like this: P, parentheses, A, and then the symbol right here. Looks almost like an upside down U or an N, and then B. That symbol right there is the intersection symbol. It basically means and, so A and B are happening. If we go back to the previous problem we were doing, we could write that the probability of choosing a chocolate and not coconut candy is P chocolate, then the intersection symbol, okay, an upside down U or an N, and then coconut with a little C up here to show complement. That's where the not comes in. Okay, so again, we're using that intersection symbol. Now remember, when we're talking about probabilities involving the word and, both events must occur at the same time. So if we look visually at a Venn diagram and a two-way table, and we wanted to shade the probability of A and B happening, what would we do? Well, first we'd shade the probability of A. Then we would look at the probability of B. And since we want the probability of A and B happening together, we're going to erase everywhere where they happen separately and only leave where they intersect or where they overlap. Now that we have a better understanding of and probabilities, also called intersections, go ahead and try this next problem here. What is the probability of choosing a chocolate and coconut candy? Now, when you find your answer, make sure to write it like this: the probability of chocolate and, again, that's the intersection symbol, coconut, should equal. Make sure you write your answer as a fraction, a decimal, and a percent. Pause the video now and give it a try. This last question is a little bit different. What is the probability of choosing a chocolate and a not chocolate candy? How do I figure out chocolate and not chocolate? Well, let's start by highlighting all the candies that are chocolate. I'll use yellow for that. Now let's shade all the candies that are not chocolate. I'll do that in pink. All right, so it looks like we're good with the visual up here. On the Venn diagram, chocolate is inside the circle and not chocolate is outside the circle. We've got our two different rows here on our two-way table. So since we want to know where chocolate and not chocolate is, where are all the spots where they intersect? It turns out there is nowhere where chocolate and no chocolate intersects. We call these mutually exclusive events. Mutually exclusive events have no overlap and cannot occur at the same time. For example, you can't have a candy that's both chocolate and not chocolate at the same time. Those are mutually exclusive. And it turns out whenever you want the probability of two mutually exclusive events, such as chocolate and not chocolate with the complement symbol up here, the probability is always 0. Remember, because there's no overlap. But what if we have a problem that uses or instead of and? Just like last time, we'll start with an example. What is the probability of choosing a chocolate or not coconut candy? Or probabilities are different than and probabilities. If I told you that I wanted a candy that was both chocolate and not coconut, then I could only choose ones that satisfy both conditions. But if you asked for a candy that was chocolate or not coconut, I could get you a chocolate one, I could get you a not coconut candy, or I can get you one that satisfies both conditions. Here's what that looks like visually. I could choose this one because it's chocolate. I could choose this one because it's not coconut. Or I could use this one because it's both chocolate and not coconut. In fact, I could choose any of these because they are all either chocolate or not coconut or both. So it turns out there are 11 out of 12 of these candies that are chocolate or not coconut. Let's see what this would look like on a two-way table. First, I'll shade all of the chocolate candies. Next, I'll shade all of the not coconut candies. Now before, when we were thinking about chocolate and not coconut, we found where these two things overlapped. But instead, when we're thinking about chocolate or not coconut, we're going to look for everywhere that is shaded, not just where they overlap. So 3 plus 6 plus 2 gives us 11 total candies that are chocolate or not coconut. And it works basically the same way on a Venn diagram. First, shade the chocolate candies, then shade the not coconut candies, and anywhere that's shaded, not just where they overlap, is included in the OR probability. Again, that comes to 11 out of 12 total candies. So that is 11 out of 12 is a fraction, which is 0.92 as a decimal if you round properly, or 92% of chocolates, or sorry, 92% of candies are either chocolate or not coconut. Now let's add in the details. OR probability is also called a union. Any probability involving the word OR is called a union. And that makes sense because we're unifying all of the shaded areas. We write the probability of A or B happening as P parentheses A, this is the union symbol, it looks like a U, and then B. So then we could have written the probability of choosing a chocolate or not coconut candy from the last problem like this. P, chocolate, the U for the union means or, coconut, with the C up top. And that's how you would notate the probability of chocolate or not coconut. The last detail about or unions is that either event can occur separately or they can occur together. So looking at this visually, if we want to shade the probability of A union B, or A or B, we would first shade A, then we would shade B, and since this is OR probability, also called a union, we're going to consider all the places that are shaded and not just the intersection. Now, try the second example here. What is the probability of choosing a chocolate or coconut candy? Again, start your response with the probability of chocolate, or, that's a union, coconut, equals, and then write down the fraction, the decimal, and the percent. Pause the video here and give it a try. Now just like before, This last question has a little bit of a quirk to it. What is the probability of choosing a chocolate or a not chocolate candy? How does that work? Chocolate or not chocolate? Well, what would it mean to choose a chocolate or a not chocolate candy? Well, first, let me shade all the chocolate candies in the visual up here, the Venn diagram, and the two-way table, shading all the chocolate candies. Now let's take a look at the not chocolate candies. Now, because this is an OR probability, I can choose either of those options. Now, it turns out because there's no overlap between the chocolate and the not chocolate, when I combine them, I get all the different candies. So when you're thinking about OR probability, remember, it doesn't matter where they overlap. All that matters is what's shaded together. So it turns out the probability of getting a chocolate or, again, union, chocolate complements, that's not chocolate, would be 12 out of 12, which is equal to 1 or 100%. So you'll always get a candy that's either chocolate or not chocolate. Let's end here with conditional probability. Now, conditional probability is a little different than anything we've done before because we're going to change which actual candies we're looking at as our group. Let's start with an example. What is the probability of choosing a coconut candy given that it is chocolate? So we want the probability of a coconut candy given that the candy is chocolate. Well, what does that mean, given that the candy is chocolate? It means that we're no longer looking at all 12 candies because we already know that we're only looking at chocolate candies. So we're going to eliminate all the candies that are not chocolate, since we already know the candy must be chocolate. So in that case, there's no longer 12 candies to look at, but only 1, 2, 3, 4, 5, 6, 7, 8, 9 candies to look at. Of those 9 candies, we now know that 3 of them have coconut. So, given the fact that we're only looking at chocolate candies, 3 out of 9 are coconut. How does this look on a two-way table? Well, we were given that the candy was chocolate, so we're going to cross out everything that is not chocolate. Okay? And that leaves us with only 9 candies instead of the 12. Of those 9 candies, 3 are coconut. So 3 out of 9 candies are coconut, given that that candy is also chocolate. What about in a Venn diagram? Well, since we were given that the candy had to be chocolate, we're not going to look at anything that is not chocolate. We're left with 9 candies again, and of those 9 candies, 3 of them are also coconut. So again, 3 out of 9 are coconut, given that we're only looking at chocolate candies. So we now know that 3 candies were coconut out of the 9 candies that were chocolate. That reduces to a fraction of 1/3. As a decimal, that is 0.33 repeating, or to round to 0.33. And as a percent, that is a 33% chance of getting a coconut candy, given that you know you're already looking at chocolate ones. Let's fill in some of the details about conditional probability. If we're given or assume some sort of information in the probability problem, then it is a conditional probability. And the probability of A, given that B has already happened, is written like this: P, parentheses, A, a vertical line, and then B. So back to the previous problem, the probability of choosing a coconut candy, given that we already know it's chocolate, would be written like this: P, coconut, vertical line, chocolate, close the parentheses. And in any conditional or given probability, our denominator or total outcomes is reduced. For example, in the last problem, instead of looking at all 12 candies, we were only looking at the 9 that were already chocolate. Now, if we were going to go back to a two-way table and a Venn diagram, how would we shade the probability of A given B? Well, since we know that B has already happened, we're going to cross off everywhere where B has not happened. Now that we only have the places where B has happened, we're going to look more specifically at the places where A also happens, which is right here and right here. When we create our fraction to find the probability, it will just be the place where A and B occurs, in yellow, divided by the places where B occurs. Remember, When we're looking at a given probability or conditional probability, we're no longer looking at the full number of occurrences. Pause the video here and give this last problem a try. What is the probability of choosing a chocolate candy given that it is coconut? Remember to start your example by writing out the probability of chocolate given that it is coconut. Again, give your answer as a fraction, decimal, and a percent.